Welcome to channel name. Don't forget to subscribe. The air inside the control room 4 of the V.I. Lenin nuclear power station didn't just feel heavy on the night of April 26, 1986. It felt charged with a strange, invisible tension that no instrument could fully capture. At exactly 1:23:45 a.m., a sound erupted from the heart of the earth. A low-frequency thud that vibrated through the reinforced concrete walls, followed by a roar so profound it felt like the very fabric of reality was being torn apart. High above the reactor hall, the Elena, the 2,000-ton biological shield made of heavy steel and concrete, a lid designed to seal the reactor for eternity, was tossed into the air like a loose coin in a fountain. In that singular, terrifying heartbeat, a pillar of iridescent blue light shot straight up into the Ukrainian night sky, ionizing the atmosphere and signaling the beginning of the worst engineering catastrophe in human history. This was the moment the impossible happened. The Soviet dream of tamed atomic energy had turned into a nightmare of fire and graphite. Yet the most shocking revelation isn't found in the flames themselves. It lies in a tiny hidden mechanical flaw within the very system designed to save the plant. A secret we will uncover later in this video that proves the disaster was locked into the reactor's DNA long before the first alarm ever sounded. To understand how this behemoth fell, we must first look at the sheer, staggering scale of the RBMK-1000 reactor. This wasn't just a power plant, it was a cathedral of Soviet industrial ambition. The RBMK-1000, or high-power channel-type reactor, was a marvel of graphite-moderated, water-cooled engineering. Imagine a structure so massive it could comfortably house a 20-story apartment building inside its containment hall. The reactor core itself was a gargantuan cylinder, 12 meters in diameter and 7 meters high, comprised of over 1,700 individual fuel channels. Each of these channels was a high-pressure pipe designed to circulate cooling water around 190 tons of uranium dioxide fuel. To put that into perspective, the energy density contained within that core was enough to power a city of millions. Yet the entire assembly was held together by a complex lattice of graphite blocks, weighing over 1,700 tons. If you were to stack those graphite blocks on a scale, they would outweigh 300 adult African elephants. This was a machine of Titan-class proportions, designed to be the backbone of a superpower's energy grid, producing a staggering 3,200 megawatts of thermal power at peak capacity. Every number associated with Chernobyl defies easy comprehension. The cooling system alone required a flow rate of 45,000 cubic meters of water per hour, a volume equivalent to filling an Olympic-sized swimming pool every 2 minutes. The steam drums, the massive separators that filtered the boiling water from the steam, were 30 meters long and weighed 200 tons each. The entire facility was a labyrinth of over 400 kilometers of piping, a vascular system of steel and heat that pulsed with the lifeblood of the atom. Engineers at the time were told that the RBMK was so safe, so robust, that it could be built in the middle of Red Square in Moscow without any risk to the public. It was marketed as the ultimate fail-safe design, a testament to the superiority of socialist engineering. It had been inspected by the highest levels of the Soviet Ministry of Energy, certified by the Kurchatov Institute, and operated by men who had spent their entire lives studying the physics of the nucleus. Yet, underneath this veneer of absolute safety and legal certification, the RBMK-1000 was a ticking clock. We are taught that massive structures fall because of external shocks, earthquakes, bombs, or storms. But Chernobyl didn't need an external enemy. The very specs that made it a mega project of the century, the massive size of the core and the use of graphite to maintain the reaction created a latent instability that few dared to talk about. The reactor was legal, it was certified, and on the morning of April 25th, it was operating exactly as it had for years. It was a flagship of human progress, a symbol of the victory over nature. And yet, within 24 hours, the perfect engineering of the Soviet Union would shatter, proving that even the most meticulously inspected machines are only as strong as the human egos and hidden flaws that govern them. We are about to go deep into the mechanics of why this unsinkable reactor didn't just fail, but essentially turned itself into a massive, pressurized cannon with no way to stop the firing sequence. The disaster did not begin with an explosion. It began with a routine request and a fatal delay. To understand the mechanics of the catastrophe, we have to look at the bureaucracy of the Soviet power grid. On April 25th, Unit 4 was scheduled for a routine maintenance shutdown. During this window, engineers wanted to test a theory. Could the momentum of a spinning turbine generator provide enough electricity to run the cooling pumps for just 60 seconds if the main power failed? It was a safety test designed to bridge the gap before the emergency diesel generators kicked in. But the regional power controller in Kiev denied the request to lower power. The city needed electricity for the upcoming May Day holidays. This meant the reactor was forced to run at half power for 9 grueling hours, a state of unbalance that would prove fatal. During this time, a silent killer began to grow inside the core: Xenon-135. Think of Xenon-135 as a neutron sponge. It is a byproduct of nuclear fission that eats the very neutrons needed to keep the reaction going. Because the reactor was running at a low, unstable power level, the xenon wasn't being burned off as it usually was. It was accumulating, effectively poisoning the engine. By the time the night shift took over, led by Alexander Akimov and the 25-year-old Leonid Toptanov, the reactor was physically sluggish. It was like trying to drive a car uphill while the engine was filled with sludge. When they finally got the green light to drop the power further to begin the test, the power didn't just drop. It plummeted to near zero. The reactor was stalling. This is where the chain of human decisions met the unforgiving laws of physics. Anatoly Dyatlov, the deputy chief engineer, reportedly pressured the young operators to raise the power back up. But to fight the xenon poisoning, they had to do something unthinkable. They began pulling out the control rods. These rods, made of boron, are the brakes of a nuclear reactor. They absorb neutrons to slow down the reaction. The RBMK-1000 had a strict safety protocol. At least 30 rods had to remain in the core at all times to maintain the operational reactivity margin. On that night, in a desperate attempt to kickstart the stalled reactor, the operators pulled out almost all of them. Only 6 to 18 rods remained. They had effectively taken the brakes off a heavy truck and started coasting down a mountain. Now, let's talk about the structural and thermal limits, what engineers call the load capacity and yield strength. In a nuclear reactor, the load capacity refers to how much heat the cooling water can carry away before the system fails. As the power began to slowly creep back up, the cooling water started to boil. In most Western reactors, steam bubbles, or voids, actually slow the reaction down because they don't moderate neutrons well. But the RBMK was different. It had what is known as a positive void coefficient. In this design, more steam bubbles meant more reactivity. It's a feedback loop from hell. More heat creates more steam, which creates more heat, which creates even more steam. This brings us to the yield strength of the fuel cladding. The fuel pellets were encased in zirconium alloy tubes. These tubes are designed to withstand incredible heat, but they have a breaking point. As the voids increased, the cooling water was no longer liquid. It was a chaotic mix of steam and spray. The angle of inclination of the control rods, the literal path they had to travel to enter the core, was perfectly vertical. But as the heat warped the metal channels, that path was becoming obstructed. The pipes were experiencing a rapid form of metal fatigue as the internal pressure surged far beyond the design specifications. The primary cooling circuit was designed for a pressure of about 7 megapascals, roughly 70 times the pressure of the air around you. Within seconds, that pressure was doubling, then tripling. By 1:23:04 a.m., the test officially began. The operators shut off the steam to the turbines. This was the point of no return. With the turbines slowing down, the cooling pumps also slowed. The flow of water into the core dropped. The positive void coefficient took over. The reactor was no longer a controlled power source. It was a runaway thermal engine. Inside the core, the energy wasn't just increasing, it was jumping exponentially. In less than 10 seconds, the power output of the reactor leaped from 200 megawatts to over 30,000 megawatts, 10 times its maximum rated capacity. The heat was so intense that the fuel rods began to shatter. The zirconium cladding reached its yield strength and burst, dumping white-hot uranium fuel directly into the cooling water. This caused an instantaneous steam explosion. Imagine a pressure cooker the size of a cathedral, being heated by 1,000 suns, with the lid bolted shut. The building itself was never designed with a containment structure, a thick concrete dome common in the West. It only had a standard industrial roof, designed to handle normal wind loads, not the force of a volcanic eruption. The pipes, weakened by years of vibration and minor metal fatigue, simply vaporized. The stage was set for the final, terrifying collapse of the Soviet atomic dream. At precisely 1:23:40 a.m., Leonid Toptanov reached for the most consequential button in the history of nuclear energy: AZ5. This was the emergency shutdown, the scram switch, designed to plunge all 211 control rods into the core and stop the reaction instantly. But in a cruel twist of engineering fate, the safety system became the detonator. Because the rods were almost entirely withdrawn, they had to travel through the full height of the reactor. The first part of the rods to enter the core weren't the neutron-absorbing boron, but the 5-meter-long graphite tips. Graphite, which is a moderator, actually increases reactivity. For the first few seconds of the shutdown, the reactor didn't slow down. It received a massive, localized surge of energy at the bottom of the core. This is what engineers call a prompt supercritical excursion. It was a poison tip on a needle meant to heal. The disaster unfolded in a terrifying sequence of just 5 seconds. Inside the reactor hall, Valery Perevochenko, the reactor section foreman, looked down from the viewing balcony and saw something that defied the laws of physics. The 350-kilogram steel caps of the fuel channels were jumping up and down in their sockets, like the lids of boiling pots. The floor was literally breathing. A second later, a massive steam explosion ripped through the core, fueled by the instantaneous vaporization of the cooling water. This wasn't a nuclear explosion in the sense of an atomic bomb, but a high-pressure steam blast that exerted enough force to throw the 2,000-ton Elena lid into the air. Imagine taking a piece of steel as heavy as 5 Boeing 747s and tossing it like a pancake. As the lid fell back down at an angle, it sliced through the reactor's vascular system, exposing the white-hot graphite core to the oxygen of the outside world. Then came the second explosion, even more powerful than the first. This was likely a combination of hydrogen gas and the final runaway nuclear surge. The roof of Unit 4 vanished in a flash of heat and debris. Eyewitnesses outside the plant described a terrifyingly beautiful sight. A pillar of blue-violet light stretching kilometers into the sky. This was Cherenkov radiation, the visual signature of high-energy particles tearing through the air. To a scientist, that light was the color of death. To the operators in the control room, who couldn't see the outside, it was just a massive shockwave that blew the heavy doors off their hinges and filled the air with dust and the smell of ozone. The human cost began in that very first second. Valery Kodemchuk, the pump operator, was likely vaporized instantly, or buried under thousands of tons of concrete and twisted steel. He remains there to this day, the only person never recovered, effectively entombed in the ruins of the pump room. Vladimir Shashanok, an engineer sent to check the gauges, was found pinned under debris, his back broken, and his body covered in thermal and radiation burns. He died hours later in the Pripyat hospital. Then there were the firefighters, like 25-year-old Vasily Ignatenko. They arrived within minutes, wearing only standard canvas uniforms and helmets. They weren't fighting a normal fire. They were walking onto a floor littered with chunks of highly radioactive graphite. Each of those black stones was emitting enough radiation to give a lethal dose in just minutes. Ignatenko would die a slow, agonizing death 2 weeks later, his body literally decomposing from the inside out as the radiation destroyed his bone marrow and DNA. The immediate response from the plant leadership was a masterclass in denial. Viktor Brukhanov, the plant director, was told the reactor was destroyed, but he refused to believe it. He famously reported to Moscow that the reactor is intact and that radiation levels were only 3.6 Röntgen per hour, the maximum his low-range dosimeters could read. The real level was closer to 15,000 Röntgen. To put that in perspective, 3.6 Röntgen is like getting a few extra X-rays. 15,000 Röntgen is like standing inside a running microwave. This lie delayed the evacuation of the nearby city of Pripyat for 36 hours, leaving 50,000 people to breathe in the hot particles of plutonium and iodine-131 falling like invisible snow on their streets and playgrounds. The investigation that followed was a battle of narratives. Initially, the Soviet Union blamed the operators entirely, sentencing Brukhanov, Dyatlov, and Fomin to 10 years in a labor camp during a closed trial in 1987. They were accused of gross violation of safety regulations. However, the 1992 INSAG-7 report by the International Atomic Energy Agency corrected this. While the operators made mistakes, the primary cause was the inherently unstable design of the RBMK and the secret of the graphite-tipped control rods. The state knew about this flaw as early as 1983, following a near miss at the Ignalina plant, but they kept it classified to save face. The disaster wasn't just a failure of pipes and fuel. It was a failure of a system that prioritized political secrecy over the laws of physics and the safety of its people. The silence that fell over the 2,600 square kilometer exclusion zone in the wake of the disaster wasn't just the absence of human life. It was the heavy, suffocating silence of a global wake-up call. The Chernobyl disaster didn't just break a reactor, it broke the world's blind faith in fail-safe technology. In the years following the explosion, the engineering world underwent a radical transformation. The RBMK 1000, once the crown jewel of Soviet energy, had to be fundamentally redesigned under the shadow of its own failure. Every remaining RBMK reactor in the Soviet Union, from Kursk to Leningrad, was pulled into an emergency overhaul. Engineers increased the number of control rods that must remain in the core at all times, from 30 to 80, effectively doubling the safety margin. They also increased the fuel enrichment from 2% to 2.4%, a move that made the physics of the core far more stable and significantly reduced the dangerous positive void coefficient. It was like adding a permanent speed governor to a racing car that had proven too fast for its own brakes. But the most critical mechanical fix was to the detonator itself, the control rods. The graphite tips were lengthened, and the design was altered so that the rods were never fully withdrawn from the core. This ensured that the poison tip effect, where graphite increased reactivity during an emergency shutdown, could never happen again. Internationally, Chernobyl led to the birth of WANO, the World Association of Nuclear Operators. For the first time, nuclear engineers across the globe, from the US to the USSR, began sharing safety data and near-miss reports. The Iron Curtain of nuclear secrecy was partially lifted because the world realized that a meltdown in one country is a disaster for every country. Yet, as we look back, the most chilling part of the Chernobyl story isn't that the disaster happened. It's that it was predicted. 11 years earlier, in 1975, a partial meltdown occurred at the Leningrad nuclear power plant, a sister facility using the same RBMK design. The engineers there reported the same positive void instability and the dangerous behavior of the control rods. Again, in 1983, at the Ignalina plant in Lithuania, the graphite-tipped flaw was flagged during a startup test. In both cases, the Soviet state chose to classify the reports as top secret, rather than admit to a design flaw. They prioritized the prestige of the atom over the safety of the people. The lessons were written in the logs of other plants, but the ink was invisible until it was charred by the fires of Unit 4. This proves that Chernobyl wasn't just an accident of physics. It was a disaster of bureaucracy, a systemic choice to value silence over science. Today, the legacy of Chernobyl is encased in the new Safe Confinement, the largest movable land-based structure ever built by humans. Completed in 2016, this massive silver arch weighs 36,000 tons, roughly equivalent to 3 Eiffel Towers. It cost 2.1 billion euros and was funded by over 40 nations. It is an engineering marvel designed to last 100 years, sealing in the 200 tons of radioactive lava and dust that still sit in the basement of the reactor hall. It is a tomb for a machine that we couldn't control, a $2 billion reminder that when we build Titan-class projects, we take on Titan-class responsibilities. Chernobyl serves as a mirror to our own human ambition. It shows us that when we ignore the small warnings and the minor flaws in the pursuit of records and quotas, we aren't just building progress, we are building a catastrophe. The disaster at Chernobyl wasn't just a failure of pipes and fuel cladding. It was a failure of the human ego. It reminds us that in the world of high-stakes engineering, the most dangerous component isn't the uranium or the pressure, it's the lie. Thank you for watching this deep dive into the heart of the zone. If you found this breakdown of the mechanics and the human cost of Chernobyl insightful, please hit that like button and subscribe for more stories of human ambition and its consequences. Now, I want to hear from you in the comments. In our modern age of AI and automation, do you think we are more or less likely to see a systemic engineering failure on this scale? Is the human factor still our weakest link? Or have we finally built machines that are smarter than our own mistakes? Let's discuss below.